All right, excellent. I want to thank the organizers for inviting me to talk and to finish out the session on exotic transients by talking about a few that we actually do see observationally. So yes, I will be talking about fast optical transients. So clearly, first off, I want to thank all of my collaborators, many of whom are in this room, without who a lot of the work that I'll be presenting here wouldn't have been possible. So clearly I'm going to be talking about things which are rapidly evolving, but I want to start off by making sure everyone's on the same page by what I mean by this. So what I'm showing you here is just a phase-space plot of supernovae. We've seen many iterations of this throughout the meeting, but what I'm showing in particular is luminosity of a transient versus a time scale. Here, this is just the time that it's above half of its peak luminosity. So for reference, this is where your typical type 1a falls in this plot. Here are your 1bcs. Here are your hydrogen-rich objects, typically shifted up to much longer timescales. And over here on this side, objects with characteristic timescales less than about 12 days or so is what I'm going to be mostly focusing on in this talk. So in particular, I want to point out that what I will not be talking about, I won't really be mentioning some of the weird type 1As that Ken mentioned in his talk, so the calcium-rich transients or the type 1AX. They are sometimes characterized as rapidly evolving, but they're just a little bit faster than this cutoff. I'm also not going to be talking about a few of the things Brad mentioned on the first day with characteristic timescales like on a day timescale. So everything lasts at least a few rest frame days, but characteristic timescales less than about 12. So the other important thing is that there's no actual physical gap separating these objects from the bulk of the supernova population. They are just objects with short enough timescales that I think it tells us something interesting about the physics of the explosion. So to see this, let's just quickly review the main processes where you get optical emission from supernovae, some of the characteristic ones. So for type 1 events, you're often powered by radioactive decay of nickel-56 synthesized in the explosion. Type 2s, you've got hydrogen recombination going on, and then in many events, we also see now that you're partially powered by circumstellar interaction when the ejecta slams into material surrounding it. So the question I want you to ask is, in each scenario, if you have a transient that is powered by each of the sources, what is the physical implications if you push that timescale much shorter? So for radioactive decay, your timescale is mostly dictated by the photon diffusion timescale, so a smaller timescale typically means smaller ejecta mass. Similar for hydrogen recombination, your timescale is going to be related to just how much material you'll have around recombine, and it's clearly more complicated for circumstellar interaction, but your timescales are going to be related to what radius that material is located at, what the changes in density are, things like that. So the important point is that in all of these cases, rapidly evolving transients are probing extremes of both the progenitor configuration and the explosion parameters themselves. So as a result, we often need detailed modeling to understand if we see one of these transients, whether it actually is just an extreme case of something we already know or an entirely new type of transient, because many of the simple analytic relations, at least that observers tend to use, break down in these regimes. So as a first example of this, I wanted to zoom in on a couple of objects down here in this region of the parameter space here. So in that region, there are a couple of very rapidly declining type 1 supernovae. I'm mostly showing you one that we worked on a few years ago, 2005 EK, in this plot where it's the colored circles, and you can see its light curve compared to other rapidly evolving events, and it just plummets. It decays by several orders of, like 3 orders of magnitude over 15 days after maximum. And it was a typical type 1 supernova, though. You look at its spectra, and it was big, broad P Cygni features. It was definitely a supernovae. I'm showing you here compared to just 2 other events. Ken mentioned O2BJ, which is quite a bit brighter, but 2010X, which Monsi published, was similar in many regards. So you have very rapidly declining events. Usually that is going to mean smaller ejecta masses in sort of the typical picture of powering supernova that we know. And it turns out there are quite a few ways you can get low ejecta masses from various processes involving degenerate objects. So Ken just gave a great overview of many of those involving white dwarfs. I'm showing you here, and there really is a plethora of incretion-induced collapse, various types of mergers, and these helium shell detonations, all of which are predicted to produce transients which have these faint, rapidly evolving timescales. In particular, the helium shell detonations, so the 0.1As, have a particularly good match to the light curves of these events. However, as Ken did point out, if you take a mostly helium shell and you detonate it, you predict that the elements in the ejecta should be mostly calcium, titanium, and unburnt helium, with a particular lack of other intermediate mass elements. However, when we went and looked at this object, both we did this with 2005 EK, and then Io Kleiser and Dan Kaysen did similar modeling for 2010X, you find something very different. You find an ejecta that's actually dominated by oxygen. And this is inconsistent with just taking a pure or mostly helium shell and detonating it. So these are likely not 0.1A supernovae in the sense that Ken was talking about. There are other ways you can get around this potentially with white dwarfs. For instance, if you do have a low mass white dwarf and you have a double detonation, maybe you can still produce this sort of thing. But another option that's particularly intriguing is that the abundances you get out of these events are actually very close to what you infer for other stripped envelope core collapse supernovae. So these may be very extreme cases of events like that. So the question is, what does it then mean if you have a very rapidly declining stripped envelope core collapse supernovae? So for 2005 EK, we were actually able to model this as being powered by radioactive decay of nickel-56. In particular, for this particular supernovae, we have a few late-time photometric points that constrain that the light curve did change slope, as you might expect from radioactive decay at late times. So this is just a model of that. And when you do simple RNet modeling with this, you infer an ejecta mass that's only about 0.3 solar masses. So this is incredibly small. In particular, you have to ask what this means for the evolution of the system. So first off, right off the bat, you know that it probably has to be binary evolution. You cannot strip a massive star that much simply by massive winds alone. However, this is the normal picture when we think of binary progenitors to type 1bc supernovae. You often picture something like this. You have your binary, the primary overfills its Roche-Lab, it goes explode as a supernovae. However, many binary population synthesis models in this regard still predict that you should end up with ejecta masses for the supernovae of about a solar mass or so. It's pretty hard to get it much below that. So we may be entering a regime where you have to push it and strip the star even more. So one possible way to resolve this is to take this same scenario, but now you have two high mass stars that will eventually explode as supernovae. And then this scenario really continues after that evolution. So you go through a lot of different processes, common envelope evolution, you know, very scary. But at a certain point here, you can possibly, in some cases, go through another case of Roche-Lobe overflow from now the secondary star back onto the compact object. This event will eventually explode as a supernova itself, and these lead to binary neutron stars, which eventually will be LIGO sources. And since publishing of some of this work, there have now been several models for what this second ultra-strip supernovae will look like, and you can get models that resemble the objects we're seeing quite a bit. So this is, we may now be entering the regime with our surveys that we are starting to probe and starting to be able to actually observe these types of events that we know must occur. However, I also wanted to point out that there are other ways to get supernovae of this sort from massive stars. In particular, I wanted to highlight a model that Io Kleiser came out with several years ago, modeling very similar types of events. But as opposed to having it be powered by nickel-56 and have a very low ejecta mass, you have a typical energy, typical ejecta mass, but you put out almost no radioactive nickel. Instead, what you're powering the light curve by is actually just basically, it's the equivalent of a type 2p supernovae, but it's an oxygen-plateau supernovae. So shock goes through the envelope, shock heats it, you cool and recombine. What's interesting about this is in order to get the timescales and luminosities for these transients, what you need is you need to have a decent amount of oxygen-rich material at a pretty large radius for a strip star. You need it to be about 30 solar radii or so, and you need like 0.3 solar mass of oxygen-rich material out there. This is not a typical progenitor envelope structure, and the question is, how do you inflate the progenitor that much? And it might be a scenario where you actually have some sort of enhanced mass loss prior to the star exploding, but then you also need to eject not very much nickel. And I think this is interesting because we've heard at several points throughout this conference more and more lines of evidence that massive stars are doing unusual things before they die. And in particular, I wanted to highlight another object, which it itself is not rapidly declining, but I think fits into this picture for some of these rapidly declining events quite well. Supernova 2013 GE, it was a pretty standard type 1c supernovae. If you looked at it from maximum light onward, you would not have predicted anything unusual. It was very normal in every way. But we didn't discover it at maximum light. We found it very early. And it had an interesting excess component of emission at early times, mostly in the blue bands, blue and UV bands. And I'm just showing you the U band here. And this is just a rough decomposition showing you this excess of emission at early times. And basically, if we assume that that excess emission at early times is cooling envelope emission, we find something very similar to what Io and Dan required for 2010 10x to reproduce via this model, you need a very extended progenitor envelope, something about at least 30 solar radii, and it's possible that the star had to eject a little bit of material before it exploded, but in this case, we did then see it coupled to a normal type 1c supernovae. So it's possible that these are we're starting to see related events, just sometimes the exact situation you observe is only the rapidly evolving event beforehand. In particular, for this object, we got 3 very early spectra of it, and that early spectra very closely resembled 2002 BJ, which was a rapidly evolving transient that Ken mentioned before. So there are several different ways you can explain these sorts of results, but it's possible that what we're seeing is an example or related process, but in a massive star that then successfully explodes as a supernova afterwards. So that was a very sort of long-winded introduction to just why some rapidly evolving transients are showing you that we really are probing the extremes of some of the progenitor stars and explosion parameters themselves. But really, ideally, we want to move beyond single objects in this regard. We want to understand what the population is as a whole and what their rates are. And that's because these rapidly evolving transients really understanding their true nature and intrinsic rate really can influence our understanding of various stages of stellar evolution. But to do that, we need to figure out how good we are detecting them in the first place. And as it turns out, this has actually been very hard. Whereas everything else on this plot that I'm showing you was sort of a characteristic example, just to give you timescales. Until about 8 years or so ago, these 5 objects were the only ones we knew of at very short timescales. And that's simply because most of the surveys we were using were optimized for type 1a supernovae and just weren't very efficient at these shortest timescales. However, as our surveys are getting better and better, this is changing. In particular, a few years ago, we went through and did a systematic search within the Pan-STARRS 1 medium deep survey. So Pan-STARRS, many of you are familiar with. It ran for about 4.5 years. It was 10 medium deep fields squared throughout the sky, and in particular, it had daily cadence, and it was a multi-band survey. So what we did was we went through and systematically surveyed the entire thing, looking for transients which occurred on short timescales. And lo and behold, when you have a survey with a rapid cadence, you find things. And so here's just a montage of some of the events that we found in the survey compared to just a typical type 1 BC supernovae in the background. And so this is what this region of parameter space looked like before we did the survey, and this is what it's looking like now. So we really are starting to fill in this region of parameter space now that we have surveys with short enough cadences that we can really start to detect these events. So what are the objects that we found in the Pan-STARRS survey? You notice right away, so it was these objects down here, which were some of the hydrogen-poor, rapidly declining supernovae that I told you about earlier. You can see right off the bat that many of these objects have much higher luminosities and are probably very different beasts. And indeed, that's true. For the sample we found in Pan-STARRS, they do show some variety, but many of them show a similar set of properties. Some of them are quite luminous. They have very blue colors. And in general, when we model their spectra, they're consistent with an ejecta that is it's just expanding and cooling, so a hot, optically thick photosphere. Their spectra are dominated by continua. Here are a couple of the spectra for the explosions in the colors here. And they all exploded in star-forming galaxies. So when we put them all together, the question is, what does that mean for the progenitors themselves? And in particular, it really highlights in my mind that many of the properties of the Pan-STARRS event are much more consistent with being powered by some sort of interaction or shock breakout and recombination as opposed to by radioactive decay. You really can't get something that is both that luminous and that rapidly evolving being powered primarily by radioactive material. So what does that actually mean? It's possible that some of these could be shock breakouts from extended stellar surface, some of what I've told you before. So here I'm just showing you in colored are a few of our events from Pan-STARRS, and this curve here, this is the type 2b supernova 1993J, which had its cooling envelope emission at early times followed by a nickel-powered peak. And some of our events, their initial decline is very consistent with that, but then you are distinctly lacking that second peak afterwards. And for several of these events, you really can put deep constraints on how much nickel is ejected from the explosion. So you need a shock breakout from an extended stellar surface that then doesn't eject very much nickel. However, some of our other events are actually quite a bit more luminous, and it's hard to be consistent with any sort of known stellar surface we see in local group galaxies. And so really, it's possible that these events are some sort of shock breakout, but instead from the stellar surface itself, some sort of extended wind medium or previous mass loss episode from the star. And indeed, there are several objects besides the Pan-STARRS 1, which have timescales that fall in this region of parameter space, one type 2n found by PTF, and several type 1bn, which are objects which show interaction with some sort of helium-rich material, that also have timescales and luminosities like this. So those show telltale signs of some sort of interaction. But again, afterwards, you have this sort of shock breakout and really not another signature of a supernova after the fact. So it's really interesting to see what that means for how these explosions are proceeding, as well as what final configuration the star is when it actually explodes. So another possibility besides these, and there have been a few models that have come out since then, is that you can get some sort of fast blue transient from having some sort of winds or outflows on compact objects or accretion disks. So one particular model that came out was perhaps you have one of these sort of failed or fallback supernovae, but from a compact, so a hydrogen-poor star, you form a black hole, some of it forms an accretion disk, and maybe a wind off of that can actually power a fast, bright transient similar to what we're seeing here. There have been a few other models that have come out as well, things like accretion disks coming from neutron star white dwarf mergers, actually neutron star mergers. There have been a lot of different predictions that have come out for how you get luminous, blue, rapidly evolving transients. But I would say we're still definitely not at the point where we have either the theoretical detail or actually the data to tell the difference between a lot of these models, and that's something I'll get back to towards the end of the talk. So the other thing that I really wanted to highlight about this was because we did a very systematic search within Pan-STARRS, which we know exactly where it was pointed at every point in time, to what sensitivity, we really can back out, at least for the events we found in Pan-STARRS, an intrinsic rate for these objects. And essentially what we do is we take the observed population we have, we model their properties, their typical luminosities, and then we inject millions of fake events into the Pan-STARRS pipeline and see what fraction we recover. And I'm showing you an example of some of that here. So that recovery fraction is what's shown on this side, and you want to be looking at the colored lines or this solid line here, and you can see that over the course of the Pan-STARRS 1 survey, even with our daily cadence, we were only recovering about 10% of the objects we injected in. So even in Pan-STARRS, we're still not yet at the point where we can recover a very high fraction of transients at these rapid timescales. So what happens though is when you invert these efficiencies into an intrinsic rate, you actually get something that's about 4 to 7% of the core collapse supernova rate. So that's important. So it's not 30%. It's not like the equivalent of type 1bc supernovae or all stripped envelope events put together, but it's also not 0.1%. This is not an intrinsically rare way for stars to end their lives, and so it's important for us to understand what is actually happening to have a complete picture of the entire scenario. So, since we did the Pan-STARRS survey a few years ago, there's been sort of a steady trickle of additional events that came out. I already mentioned very briefly, there was a recent paper by Isaac Shivers that came out on supernova 2015 U, which is a luminous event. It is a type 1bn. They see very narrow hydrogen or helium emission lines showing signs of interaction with that event. And again, it's luminous. It clearly has signs of interaction. They could put a pretty deep limit on how much nickel was associated with the event. There have then been a few other things that came out. Ayer Kavi had a paper where they actually went about this in a different way. They went out looking for events that occur in a luminosity range in between normal supernovae and superluminous supernovae and see what types of transients they pull out. It turns out some of what they found was 4 events that have very rapid rise times. And for 2 of those 4, they also show sufficiently fast declines that we would have classified them as rapidly evolving transients of the type that I am showing you here. So this is just probably a little bit hard to see, but this is just rise timescale versus peak magnitude. So the Pan-STARRS events are all in this region here, and then their events over here. So they're slightly longer timescales, but they're also much more luminous than ours, and it's possible that this is now representing a continuum or an expansion of this class of events, even beyond what we saw before. There's then also some very rapidly rising transients that were found by the Subaru HyperSupremeCam survey that came out. And again, some of these might be consistent with just typical shock breakout from red supergiants, but other ones are much more luminous and similar to our Pan-STARRS events and may actually be an indication of shock breakout from an extended wind around a star. So I think I'm coming towards the end of what I wanted to say. I just wanted to give some slight prospects on where we are going forward from here. So really what we're finding is that now that we have surveys with short enough timescales, there is a large range of types of events that occur on these short timescales. It really is a type of explosion that's happening that many of our surveys just weren't sensitive to before. But there's a lot we don't know yet about what these transients actually are. And I think there are two things which can help us with that. You know, of course, as an observer, I want more quantity and I want more quality. So I want to talk about each of those very briefly. So going back to this plot of the efficiencies with which Pan-STARRS was able to pull out the rapidly evolving transients in our event, in our survey, there's really, even in Pan-STARRS, which had a daily cadence, albeit shifting between bands, we're only peaking at about 10%. And that's a little disingenuous because that's for the entire year, whereas any given field is only in season about half the time. But even our in-season efficiencies were only peaking at about 25%. We were missing a lot of objects. And when you dig into that, there are a couple things that factor in. And I think that could help going forward as we design new surveys, that we really could design them better to be able to pull out events of this sort. First, it really is cadence. Part of what hurt Pan-STARRS in doing this, although it's been able to recover more than any other survey to date, was the fact that it was switching through bands on a night-to-night basis, so it made it harder to recover good light curves in multiple bands, which is what I used to pull these out. But really, that was secondary to the effect, which was weather. A lot of what killed our efficiencies in Pan-STARRS was simply nights that we lost due to weather or maintenance, because when you're looking for things on rapid timescales, it just ends up killing a whole week if you lose just a couple of days. And so really the only way to mitigate that is to do surveys where you start to move to multiple sites. And so starting, I think that's in a direction that several different surveys are going, or at least exploring now, because that's really the only way you can accommodate for weather, because you can't at a single site. And second then is just multi-wavelength and late time follow-up. If we really want to understand what these events are, right now for at least the luminous and blue transients from Pan-STARRS, really all that we know is what's occurring in these 20 days around maximum light, because that's the point where they hit the detection limit of Pan-STARRS, and most of them are at moderate redshift. So, and over that time scale, they really are hot blue, optically thick, expanding gas. And so there are a number of different theories that can try to accommodate that, but many of these should diverge at late times as you get things like continued interaction, signs of any radioactive decay from a supernova on, or just that there's no additional power source. And spectra in this region really will be helpful, and I think that's something we can do as the next generation of surveys turn online. We can start to find much more of these much closer. And similarly with multi-wavelength emission, there really hasn't been any to date for any of these rapidly evolving events, and to do that we need to detect them in real time. So thank you very much.
So I realize most people that work on supernova probably understand this, but I just wanted to clarify some terminology, because there might be some confusion for the general audience, that there's kind of two distinct events. There's the shock breakout, where you have a flash of light where the shock first becomes optically thin, and then you have the subsequent cooling of this shock-heated envelope. The stuff that Elizabeth was working on is more of this actual flash itself, where you're just seeing this burst of light, whereas everything that Maria's been talking about is more of this shock cooling, where now you have the photosphere backing through the envelope as the stuff's expanding and cooling. So they're distinct pieces of physics in the explosion.
Yeah, most definitely. And so everything here would be a case where, exactly, it's the cooling of the envelope after the fact. After it's shock heated, it will have to cool. And depending on the envelope structure or various things like that, often that is what is observable in certain situations here.
Just mention quickly, to add to the zoo, some of the things I showed yesterday could give you
the fast
10-day, 10 to the 43 erg type 1b structured light curves. Mm-hmm. Not 10 to the 44, but 10 to the 43.
Yeah, and a lot of the Pan-STARRS ones are right around 10 to the few times 10 to the 43 as opposed to 10 to the 40.
Good candidates. No radioactive tail, but there could still be a tail from the collisions continuing.
Yeah, so it would be interesting there to, again, find them a little closer, because with pan-stars, because most of them were at redshift of 0.3 or so, we probably don't probe deep enough to see because I think your continued tail was at like 10 to the 40, 10 to the 41, something like that.
It's quite model dependent, depends on what it's running into.
Yeah.
So for the oxygen-rich things, have you thought about WO stars for possible progenitors of those? I mean, we know they exist, and they're pretty low mass by the time they reach that phase.
How massive are they actually?
A few solar masses.
Okay,
and then
so
if
they could-
some of that goes into the neutron star, you've got maybe a very small mass of oxygen.
Okay, so it could then just be a single star that you strip that, well, if that's how you get the...
We don't know how you get them, yeah.
Yeah.
But I guess for that, doing radio or X-ray follow-up would be really important.
Yeah.
Because they have strong winds.
Yes, yeah, definitely.
Hi. I was wondering if you've investigated the possibility that, or this is related to late time follow-up, that these are kind of these like pulses before explosion, and if there's any possibility of seeing that in the late time follow-up, because I guess you don't know how much longer to wait for a
How
supernova.
much longer to wait, yeah.
And also like related if pre-explosion imaging shows you any sort of progenitor or anything like that.
Yeah, so in terms of what's been done so far, so for the pan-stars events, we do have 4.5 years worth of light curves for all of them, and I can say that we didn't see either any pre-explosion or post-explosion outbursts during those 4.5 years. But yeah, it's whether that time scale is appropriate or whether, you're missing like when the field goes behind the sun. And in terms of pre-explosion imaging, it's similar for the events we have so far. Most of them are at redshift of 0.1, 0.2, and so we can look at their host galaxies as a whole. They are star forming. The offsets within their hosts are pretty consistent with typical core collapse supernovae, but that's most of what we can say with the sample we have so far. But that's why, hopefully with the next generation of surveys, we can start detecting them much, much closer, so we can do that in more detail. Yeah.
Just a quick question. In retrospect, had you only done 2 of your 4 filters, could you have done as well? Suppose you did just GNR or GNI or something instead of GRIZ.
Yeah, I mean...
Speeded things up, but what would the recovery rate have changed to be?
Oh, would the recovery rate have changed? So if you design this, you could... Yes, it could have changed, because then if you took that time to do shorter cadences, it would have been better to that.
Yeah,
and
that's
I would
the question.
want still at least, ideally, I would want at least 2 so that you could get the
Sure.
colors, because especially in these, there is significant color evolution over them, and they're quite hot at early times. So it's useful information to at least have color.
Okay, so I've got a question. In terms of cadence, the new microlensing surveys go very quickly, but did they not go deep enough for you? Is that the, or might they actually be very helpful?
No, actually, some of them might be very helpful. There's one in particular that's, well, or I don't know if in their design as a microlensing survey with that cadence, but there are a few. There's actually one called KMTNet, which is coming on, Korean Microlensing Telescope Network, which is one of these that it's put its telescopes at multiple sites, and it's something that you could design a sub-survey within that would be very good at that.
Okay, Sri?
Yeah, I want to return to the point raised by Josh. I think a lot of time domain people don't know how to do surveys correctly, in my opinion, because the ones they do know to do correctly are 1A, but that's an experiment. It's a very definite experiment. There's a goal. You can even run a chi-squared on a nightly basis and reject all things that are interesting and stick with 1A, and that's what they do. So if you really want to do a time domain survey, the stress should be on the word time. You should do it in one band. One band means there will be a selection effect. But life is full of selection effects and biases. And to ignore that is like, simplest word is stupid, I think. Anyway, so once you find a transient, you don't need the discovery machine. You can transfer that to another telescope to get the colors. And that's how you multiply telescopes instead of adding or subtracting by doing multi-band surveys.
I would say that this is one of the situations where you have a slightly larger compromise, just because they are rapidly evolving, and the rise is when a lot of the interesting color evolution is, which happens over a day or so. But yes, you're completely correct. That is, if you want to find more of them, that is a compromise you often have to make.